NMR techniques in unconventional characterization. Dr. Shi is the NMR Senior Advisor at Code Laboratories. He received his PhD in physics in solid-state physics with emphasis in NMR relaxation from the University of Kent and Canterbury, UK in 1994. He has been focusing on developing new NMR techniques, permeability models, and petrophysical data processing for unconventional type rocks, such as oil and gas shales, since he joined Core Lab in 2012. Dr. Shi serves as a member of technical committee, past president of NMR SIG, and the current VP of Technology elect of SPWLA. So welcome, Dr. Shi, and just a quick reminder that at the end of the session, we are having a session for Q&A. So welcome and all yours, Doctor.
Okay, thank you very much for the nice introduction. And I'm very glad to do some work for your student chapter. So both Carlos and Zoya are good friends of mine. So we know each other pretty well. Today, I'm just gonna represent the paper I presented last year in 2023. And so this is a so-called distinguished speaker program. So I'm gonna do it again. So give you a little bit taste of the NMR for unconventional reservoir characterization work. So like a title says, it's kind of a latest development in this world, and give you a little bit broad review of what we can do for the unconventional type rocks like shales, etc. Okay, so this is a very simple introduction. So when we're dealing with unconventional shale rocks, so the property of a shale, people already know that. It's a nanometer scale pore sizes and ultra low permeability. We're talking about nanodarcy perm. So that's why we need to have a fracking. And the fluid in the rocks, and they have a low mobility. We call it movability or mobility, and the producibility. So it's very difficult. So this is a part of the reason, and we call this kind of a reservoir unconventional. So unconventional, maybe speaking from two parts. One, it's the reservoir very tight. And secondly, is from a producibility point of view. So it's not easy to produce, then it's unconventional. So that's a kind of a definition. People hear some of them doing the NMR measurement before. So you do the conventional NMR core analysis, but when we apply the same technology or techniques to the unconventional, so we have some difficulties or challenges. So difficulties, examples like it's very difficult to clean the sample. So we all know that. Two parts, pore size too small, and the permeability too low. So if it's not impossible, it's gonna be very difficult. It's gonna take a long time to clean the sample. Secondly, it's difficult to introduce fluid back to the rock. So once you remove fluid from the sample, you try to introduce like a resaturate sample. It's very difficult. And sometimes when you think you resaturate a sample, it may not be the same as you had a sample as received. And also the problem with the unconventional is the existence of all kind of forms of hydrocarbons or even the water in different forms. So you have a gas condensate, you have a light oil, you have a oil, heavy oil, you have bitumen, or sometimes you have a kerosene. And water, you have a pore water and the carbonary bound water, or you have a clay bound water or clay structure water. So for NMR work, we typically use the 2 megahertz. This is in the past, people using this kind of techniques for many, many years. The reason for that is that the downhole logging tool is a low frequency at about 1 megahertz or below. Nowadays, maybe close to 2 megahertz. So this is one we call it low field, low frequency NMR. And with this kind of low field or low frequency, it also has its limitations. And the biggest limitation is low sensitivity. And for the unconventional rocks, we want to get a signal very, very presentable. So that means you need a lot of signal to noise. And for the measurement, if you want to get a good signal to noise, you want to do multiple scans to average out noise, okay? So in the Shale evaluation part, we're using so-called a little bit higher frequency, for example, 20 megahertz. Some people using 12 megahertz instead of 2 megahertz. So we use 20. So that's why, and in this work, we focus on using the higher frequency. So this is the example of some NMR data on the top here, and people probably comfortable with is a so-called conventional sandstone. So you get a T2 distribution. This is a T2. This is a so-called incremental distribution. So in this case, you can see this is 100 milliseconds. This is 1 second. So the major peak is about 300 milliseconds at this point. So the majority of signal is in this part. So this is a so-called conventional data, all look like it. And for people just started NMR work, they'll just remember one physics, and that is NMR T2. This is a T2. It's a measure of molecular mobility. Just remember this simple rule. So the more mobile the molecules, you will get a longer T2. So that's kind of a correlation. So for example, here you have a T2 at 300 milliseconds. T2 here is about 20 milliseconds. T2 here is about 1 or 2 milliseconds. So the longer T2, the more mobile. So from that, we can tell, because this is a brine in the sandstone, so you get signal from this T2, and that means you have a molecules, water molecules, and they're very mobile compared to these two. So that means if you can translate into the pore sizes, this is a larger pore size, medium, and a small pore size, or even bound. For example, clay. So sometimes people call this clay bound, and that's why you do that. Okay, but for the unconventional, the story is different. Okay, so you have a major peak. This is a 0.1 millisecond. Major peak is below 0.1 milliseconds. You have other small peaks over. So that gives you some kind of challenges, because like we just said, T2 is a measure of a molecular mobility. So this is a mobile molecules, this is immobile. So maybe in the solid form, or maybe in the very thick, heavy oil, or maybe it is in a small pore. So the pore size is very small. Another challenge is when we do an NMR measurement, we have to select the so-called interaction spacing time to do the T2. So with the unconventional samples, so with different interaction spacing time, you get a different responses. The longer T you use, and the signal getting dropped, and also the T2 distribution changed. So the reason for that is because with a longer interaction spacing time, you are missing the front signal, because when you start acquire data, this signal already disappeared. So that's the reason you don't get it. So for unconventional work, we normally use a so-called two-dimensional T1, T2 mapping technique to measure the sample T1 and the T2 simultaneously. So this is a T2 direction on the horizontal axis, and this is a T1 direction. So then we get so-called correlation map. So in this map, how to read it? This is a one-to-one line. So with the theory and also with some experimental approval data. So this region, the yellow rectangular region, most likely it's going to be the water signal. This red circle is the oil signal. And this one is maybe solid organics like a bitumen or oil in small pores. And this part is complicated, maybe from a structural water, and maybe from hydroxyls, maybe from the water in clay layers. So this all kind of in this region. Okay, and if you look at these peaks on the T1 side, you have a one peak at about 1 or 2 milliseconds in this region, and another peak is just below 100 milliseconds. So you can tell, and this is oil signal, this is water signal. If you look at the T2 alone, you get a peak, like these 3 peaks. So you cannot separate water and oil. So it's here, you cannot separate the solid organics and the clays. So that's the reason we're using 2D mapping technique, try to separate the water and oil signal. And also from theory, and T1 is a frequency dependent, the frequency of the instrument. So that's why we're using a higher frequency, 20 megahertz, to separate the water and oil. If you use a lower frequency, like we're going to see next, and this is the 2 megahertz, this is a 23 megahertz. On the same sample, we do the mapping measurement. So you can see 2 peaks on the T1 direction, clearly see 2 peaks. But for the low frequency, 2 megahertz, this peak squeeze together. So it will be difficult to separate these two. But for this case, it's okay, just about to see the separation. But imagine the oil region getting larger, they're probably going to merge. So that's why I draw the cartoon here. For the 23 megahertz, you have a water, oil, solid organics, and bond clays, etc. But at the 2 megahertz, they all squeezed together. And for the log sometimes the frequency even lower, and the resolution is poor. So you get all signal just along this region. You cannot separate them. So that's give you another question to think. So when you do machine learning, you only have a T2 data, and the people say you can using some algorithm to separate water and oil signal from a T2. Do you think it's possible? Or do you have to use a different technique, for example, 2-dimensional measurements? So you have to think about that. And with the higher frequency 2D measurements, and one first application we can do is we can monitor the sample change. We all know the shale sample, and if you drill out of a well, and it will take some time for the liquid inside the shale to evaporate. But how quickly, how slow, and what's the dependence of the evaporation? So we can study with NMR. So this is one example. We take a fresh sample and just drilled, and from a well side, we take a sample to the lab, we do the NMR measurement. That's how we get it. So after few weeks, the signal changed. This is the same sample and using the same scale, and the field changed. Even the sample weight also changed. So you can see the change fast in the first 10 days. So the weight changed from 38.35 to 38.1. So you changed maybe 5% or even more, close to 10% in a few days. And this change, not the rock change, it's liquid inside the rock changed. So from NMR data, we can see not only the oil evaporated, this is oil signal, this is the water signal, also the water signal evaporated. So when you have a water signal evaporated, the T1, T2 of the signal, in this case, will be moved down because the water left behind is immobile water. So we remember T2 is the measure of molecular mobility. If it's less mobile, so T2 will be shorter. So that's why this signal moved to the corner. So that's the case for this measurement. And we also see the example, and if you have a sample you want to crush, because nowadays in the laboratory measurement method, we often use the crush method to clean sample or to do other measurements. So what happens during the crushing? So this is a comparison. So you have a intact plug sample in the laboratory. We will normally measure plug sample. So you see this is clearly a lot of water in this case. And after crushing, we measured again. You can see signal changed from this elongated shape become a shorter elongated shape. So that means you lost some water during the crushing. So when people doing the crushing, you're gonna question them, okay, what you want to do with the crushed sample. If you want to measure saturations, your saturation changed. And also when you do the saturation measurements, if a sample is not fresh, so what you measured is at that point saturation, not a saturation downhole. So that's an important message we get from here. Okay, and with the same techniques, 2D measurement, T1, T2 map measurement, we can monitor the change after liquid flooding through the sample. So this is the sample before the flooding, this is after. So we try to simulate oil production. So we flood sample with a light oil, lab oil. And afterwards, you can see a lot of oil being removed. So you still have some oil left behind. But most importantly, you have this region. We know this is a heavy hydrocarbon, maybe bitumen, maybe heavy oil, maybe oil in the small pores. After flooding, it changed. And so is the water. That's why when you do the production, you some water produced. So that gives you another way to use the NMR to do your work. And because 20 megahertz is very sensitive to do small sample measurements, we don't have to use the plugs. So we can measure the drill cuttings. So this is one example. So we take some drill cuttings, do 2D measurements. You can see a lot of oil, water signal in this case. You also see some trace of oil and some solid organics. So what this data used for, and we can compare to the plug data. This is a similar depth, it's from the same well. Now you can see the signal shape or the saturation may be similar. So that just give us the opportunity to take use of the cuttings, because the cutting is almost like a free of charge. So you can use cuttings to do a lot of work. So that's another example. One more example is, like we said earlier, so if you have a sample and already in the lab for a number of months or year, and you want to restore the original conditions. So one way we do it is by resaturate sample with a different fluid, right? So this is an example. So same sample and being dried in this case. So dry in the oven at a low temperature. Dry, then we saturate on the left with oil, on the right with brine. So you can tell, and the saturation process takes a long time. This is 21 days still going on. If you look at the number, this is the total NMR measurement, how many milligrams in this signal, from 65 to start with, all the way to 116. And the same for this one. And a similar sample size and a similar sample, and you have a 64 milligrams signal to 126 milligram water. You can see water can get into this place, easy to see where they stay. And in the same time, you can see originally there's nothing here, but you also see some water moved into there. So then you're probably gonna ask yourself, okay, why the water going there? It's not going there. Most likely, it's initially you have some water in this place. The water probably gonna replace some of oil, make the more oil move to the region they're supposed to be. So that's to give you another example for NMR applications. So you can do the saturation study, try to understand when you saturate the shale sample. And one question you need to ask is it 100% saturated? How are you going to confirm that? Okay, so people normally do start with a sample and try to measure porosity. And then you saturate with brine or oil to see if you can reach 100% saturation. And we can use NMR to do this monitoring. And another application is a combined NMR work. This is a more advanced NMR work. Instead of using so-called T2 measurements, CPMG technique, we directly using so-called early time acquisition, and people sometimes call FID, free induction decay, or using the solid echo method to acquire very early time signal. So if you look at the scale here, that's the 10 to minus 3. So that's a 0.001 millisecond. That's a 1 microsecond. Sorry, this is 10 to minus 2. So 10 microseconds to start with. So 10 microseconds and a decay all the way to 1 millisecond. And so this kind of a decay. So here is an example of the kerogen study. So we take a Green River Formation kerogen, is an outcrop, and then we measure NMR. So you can see this is NMR data. Instead of following exponential, we fit the signal into a Gaussian plus 2 exponentials. The Gaussian here is in blue, first exponential in green, and another exponential in red. So this is how we do the analysis. Then we do the so-called hydropyrolysis to mature the kerogen, the sample. So then we remove the oil produced and dry again to measure the rock sample again. So you can see the kerogen Gaussian part from this height 150 to less than 100. The green part from 200, almost the same, still 200. And then we still have a little bit red increase. And not only the green increase, also the T2. This is the T2, move to the right. So that indicating when you do the maturing process like a hydropyrolysis, and you speed up kerogen oil production process. So the kerogen produced oil, and in the same time, the maturity increased. So at the 300 C, we do the same at the 330 and the 360. You can see the green part move away from the blue, and the height also change. So that just indicating some oil produced and the maturity changed, and the mark can detect the change, measure the change. So that's just give you example. So use NMR combined with the geochemical analysis, and we can get kerogen properties directly measured by NMR. And we can also measure other different formations to do the work. One other example of NMR application is try to use NMR to calculate the so-called activation energy. So if you studied chemistry, you understand. So for the molecules to move from one state to another, you need to overcome the activation hump. So NMR can be used to do the activation energy measurement. So this is a T1, T2 map from Eagle Ford. You probably know the Eagle Ford. You can see Eagle Ford, there's no water in this. You probably have some very, very tight hydroxyl inside. So with the sample, we imbibe some oil into the sample. That's why this oil signal is very strong. And then if we just focus on this region, so we circle this region, and because there's no water, the oil is just the hydrocarbon. So we don't have to do the 2D measurement. We can just using the T2 to analyze, because the T2 is the measure of the molecule mobility. Okay, so we circle this and we do the T2, we just plot the T2. And then we do the measurement at a different temperature. So from a room temperature all the way to 100 degrees C. And you can see the T2 moved. Probably you don't see that much move. But if we plot the T2 value and then we plot the T2 value using the log scale against the temperature, and we do some transform here. So 1000 K divided by temperature. So we get this a straight line. this is follow this so-called T2 is a measure of mobility. Tau C is so-called chemical molecular correlation time. Okay, so the longer correlation time, the less mobile. So this is the inversely proportional. That means, so the shorter correlation time, more mobile, the longer T2. Okay, and this tau C follows the so-called Arrhenius equation. So this is the Arrhenius equation. And in the Arrhenius equation, and there is a EA term. EA is called activation energy. And R is a ideal gas constant. So from here, we can, using the NMR measurement with the temperature change, you can calculate the activation energy. So in this case, so activation energy gives you the indication and how easy or how difficult you can produce oil from this well or reservoir. So that's one application. This is more towards petrophysics or even physics measurement. And it's kind of one of the fundamental properties we can measure through NMR measurements with the temperature change. So you can see temperature from a room temperature all the way to 100 degrees. So we get this very nice straight line, which follows Arrhenius equation. Okay. Another example is what's the oil producibility? How are we going to measure it in the lab? So let's say you have a rock sample, shale sample, and you try to understand where the oil was located in the data or in the sample, and how you're going to produce it. So in this case, you have 4 samples. We did the work, and then we use, as received, we get these 4 samples. You can see this is a water signal, and you have a lot of oil here, but not much oil in these 2 samples. So what we do is measure it as is, and then we do a simple crush and heat it. So you measure it again, you can see we lose some oil, and you crush to the fine particle size, and you measure it again, so you lose more oil. So this oil being measured, and then you using some solvent to remove some oil. You do it again. So after a few steps, and you get this work measurement. So this has been published in OTEC conference. So with that, you plot the change in the T2s. So you can see clearly there's a change, the trend going down. So this is the amplitude going down. Then you can kind of produce this 2 peaks system. So, or maybe 3 peaks. So the red one, we call it the free oil. So in the open pores, easy to be removed. And the blue one is called free oil in the closed pores. So it's a pore oil. So if you crush to the smaller particle sizes, and you can produce this oil. And these dark ones can be called adsorbed oil. So it's been adsorbed on the surface of the pores. And the black one may be correlated, associated with kerogen. So it's gonna stay. So with that, I'm gonna give you kind of indication how easy or how difficult oil can be produced. So that's another way to do the lab procedure to understand your oil property in the shale samples. Okay. And now there's a lot of lab analysis and even being applied in the commercial analysis. For example, this is another example, is you compare NMR measurement and intact plug with crushed, as we mentioned earlier. So when you crush sample, so your liquid gonna lose because of evaporation. So this is a lot of a sample, and we crush into the different sizes. S for small size, M for medium size, L for large sizes. So the larger the particle size, the less loss. The smaller particle sizes you crush, you lose more liquid. This is easy to understand because you have a large surface area opened, when you crush to the smaller particles. But it has other factors. For example, this one lose less than number 2 sample, and the number 1 sample even lose less. So it's not just the size, and maybe another factor like the formation itself, and also clay content as well. So this is worth to study and to understand what's going on. And we also do the comparison. People probably nowadays are using a lot of so-called GRI, so stands for Gas Research Institute method to do the crush sample analysis. So you have a tight samples, rock samples, you crush into certain sizes, and then you go through this so-called Dean Stark extraction. So try to remove all the oil and the water, and then you do the analysis to calculate the saturations, okay? But with some samples after Dean Stark, you can see you still remain some residual liquids in the sample. Some are more, some less. So how you going to judge your Dean Stark method is the method to do the saturation measurement. So you have to ask yourself a question. So is that method reliable or trustable, or you have to do some modifications? So the answer to that part is we use a combined technology to do this kind of a measurement, because for the reservoir engineers, they need accurate porosity, saturation, permeability data. So in the lab, we need to do that precisely, provide accurate data to them. So we combine NMR, Dean Stark, sometimes pyrolysis, sometimes XRD, to get all kind of data, and then we combine to produce the whole picture of the results. With that, and give you some conclusion. Yeah. So latest development, especially in last 10 to 15 years, and the more and more higher frequency NMR measurement, 20 or 23 megahertz, being widely used. So if you do some literature search, and more people start using this, doing this work. So I started in Colab 2012. So I started introduced high frequency NMR into this world. So first a few years, people recognized the uses, but nowadays people understand this is the best method to do the shale analysis. So in OTEC conference, so they set a session called a high or low frequency NMR because of that. So we see a lot of applications can be done using the so-called T1, T2, 2D mapping, and to do a lot of petrophysical property measurement or evaluations. And for the future, especially for you students doing the PhDs, and should have an open mind, how you're going to apply NMR techniques for your work. So for example, you want to do shale gas or gas condensate, and how the NMR will see this. And oil interact with kerogen. For example, if you have a source rock with the kerogen inside, you saturate with the oil, so what kind of a response you're going to have? Or if you saturate with brine, do you get the same saturations? So you have to understand that. And especially another part is clay and clay-bound water. That's the most important part. And this is a tricky part as well. So we need to have a NMR method look into that. And also, people want to understand porosity and the saturations. So one biggest question people keep asking is bitumen part of porosity or not? So that's a big question. You have to find a way to answer it. And do the oil enhancement and or enhanced oil recovery, and NMR can play a big role in it. So you can use different techniques to do the oil enhanced oil recovery, and then you want to see the effect. So in the past, for the petroleum engineers, so their work is try to measure what you put in and what you come out of the rock. Okay, so what happened in the rock? there was no way to measure it, but NMR can provide such a way. So you can measure what's remaining in the rock and what has changed in the rock. And especially in the future for carbon capture utilization and CCUS, and NMR can play a big role as well. So it depends on how you want to use NMR and what you want to measure. And the biggest message for you to carry back is when you do machine learning with NMR data and ask yourself a question. So if the T1 or 1D, T1 or T2 distribution, so 1D, T2 distribution, enough for your machine learning, okay? You may feed the machine with a lot of data, but data either is incomplete or data itself is not decisive. So then your machine learning model may not be that accurate. So that's the keep in mind. And when you do the machine learning part, building models, so you need to understand what you really get. With that, thank you very much. And now ready to answer some questions and hopefully to see you in next student paper competition and the next conference. Okay.
Okay, thank you very much for the amazing presentation, Dr. Shi. Yeah, now we are open to questions. Feel free to unmute your microphone or send into the chat.
Please.
Can I ask a couple of questions, Harry?
Sure.
So the first one, when we do the T2 inversion from the magnetization decay, generally our assumption had been that they are exponential, and that's how we do the inversion. Like for I'm talking about traditional 2 megahertz magnetization decay.
Mm-hmm.
You showed a slide where you are actually taking Gaussian and then two exponential components. Is there a reason that the very initial T2 times it would be Gaussian, like in this high frequency NMR?
I don't quite understand your question. So
can you, yeah, I think there was a slide where you showed those peaks.
Okay, let me go back there.
Back, yeah.
Here, right?
Not this one, not this one. Forward. Yeah, that one. Go back.
This one?
One more. Go back one more.
Here.
Yes.
Okay.
So here you are fitting the Gaussian in the very early T2 times, right?
Yes.
So any particular reason, like did you guys like see that's the best fit, or like?
Well, that's a very good question. That means you paid attention to it. Well, this is a NMR basics. And so we don't use the so-called CPMG to do this data acquisition. Instead, we use the so-called solid echo. So solid echo is designed to capture early time data. So I didn't have that diagram ready here. So when you do NMR measurement, you use a pulse. After pulse, there's a period time we call it dead time, because at that time, during that time, the instrument is not capable to acquire any signal because there's so-called coil rain down time. So that's why we call it dead time. And during the raining down time, and there's no meaningful data can be acquired. So we have to wait. The wait time for 2 megahertz, normally we're talking about from 30 to 50, even 70, 80 microseconds, the time. And you can make it a little bit shorter, but still in 20 or 30 microsecond period time. But if you look at the data here, this is a decay time. And I try to read. This is supposed to be so-called, if you take this as a 0.001 microsecond to start, and it takes about less than 10 microseconds for it to disappear. Let me try to see. This is a 0.1 millisecond. Okay, this is a 0.1, this is a 10 microseconds. So takes about 20 or 30 microseconds, the signal completely disappeared. Okay, so for your 2 megahertz, when you do CPMG, your first data point, and let's use this as an example, is a 0.2 milliseconds.
Yes.
So that means here.
Yeah.
In this region. So that means you missed all the signal in the front. And in this case, you probably don't see much here. So the reason we use this is we try to capture early time NMR signal. So I'll start from 10 microseconds. So with that, you can see the fast decay. We told you before, and the fast decay means less mobile molecules. So that's in the kerogen. And we all know, and from NMR, this is because the behave of a solid diffusion, or we call it motion, and the decay curve no longer follows exponential. Instead, it's a Gaussian. So that's why we fit the Gaussian and exponential combination to describe this decay. So you can see the fitting is pretty well with this. So this is not normal NMR T2 measurement. Instead, it's an early time decay, and specifically for so-called short T2 components. If you look at these T2 components, this is about 10 microseconds. This is less than 0.1 millisecond. This is 0.1 millisecond. So 10 to 100 microseconds. So the maximum here is 50 microseconds. So 10, 20, 30, 40, 50, this kind of region.
Yeah.
So they are very short T2s. And the reason for its multiple components, because it has multiple components. For example, if we're talking about the kerogen, which these two represent the kerogen, and if you study chemistry, you probably understand in kerogen, you have two different chemical groups. So one is more mobile than the other. The more mobile means that they don't move around. They do this rotational motion. And one's called aliphatic, the other called, and I forgot the name again. So two different molecules, and you can use the blue and the green to describe it. Remember, the longer T2, this is the T2 position, and the more mobile. So if you have a more matured kerogen, so your T2, the blue part shall be remain, but the height will be short because this is a kerogen. So you can call it the backbone. And the other part is produced, maybe like a kerogen-like, bitumen-like organic matters. So that's what we give you. And for the red part, it could be the residual oil produced and all some water not being dried off. So that's why you see a little bit residual there. So that gives you a kind of work to do the geochemistry study.
Thank you, Harry. Thank you.
Okay, good. You said you have 2 questions.
Yeah, I'm just waiting. If others have questions, I'll come back.
Okay.
Yeah.
Mm-hmm. Thanks, Harry. I just have a sample question regarding the crushing procedures for your sample and measuring NMR after each crushing step. Do you have any standard procedure for the crushing? I mean, regarding the sizes, the mesh sizes you are using to represent large, medium, and small samples?
Yes. If you go to that specific plot, this one. So we have selected 3 different sizes. The reason for that, to try to understand when you crush sample, how much the liquid evaporated from the sample. So the larger size, we probably just like simple crush. The piece is pretty big. You can call it like a small pinky size. And the medium is a 440 mesh size. Measure 4 to 40. The small is so-called a GRI size, is a 25-30 mesh. So if you measure the dimensions of the particles for the 25-30, it's about 0.6 millimeters and average dimensions. So this is described in the GRI procedure. So people use different crush sizes to do the measurement. But in a lot of places, people nowadays try to mix different sizes for different purposes of a test. But if you want to do NMR measurement, basically you don't need to crush, because NMR can measure any sample in any shape, any color. So why it's better. The reason for crushing, we want to compare with the GRI or with another, with so-called crushing method. So that's the reason. Okay.
Thank you.
Okay, Harry, so there was this activation energy slide that you showed.
Yeah.
My simple question on that is, so the T2 logarithmic mean you are taking for calculating the right-hand side, it will be within that region, right? Not the total T2
Correct.
logarithm.
Yeah, with a circled region. So that means we pick up this oil signal and plot it here. So just that region.
Okay, so you're discarding the other components and everything,
Right.
just that particular region. Okay,
Yes.
that makes sense.
Yeah.
Last question. So do you think like the high frequency NMR is going to replace the like is there any limitations that you would want to point out, or you think that in future the high frequency NMR is just going to replace all of this standard frequency NMR?
No, I don't think so. High frequency NMR is probably better for shale analysis. The reason being, if you look at the map here, so all the water signal gonna along this line, the oil signal gonna be along this line, so a little bit tilted to that. If you look at the so-called conventional samples, so T2 will be in this region. So both water and oil, and they merge. So there's no benefit of that, because the reason we're using high frequency NMR, we try to separate the water and the oil signal. So if they merge, so there's no benefit for that. That's one. Secondly, and with a higher frequency, a higher and magnetic field strength, and you tend to have a so-called stronger intergradient. So magnetic internal gradient across the sample, because you have a lot of so-called impurity in the sample. Those impurity may be paramagnetic or even ferromagnetic. So that means you have, for example, a lot of iron in the sample. So the iron can interfere with your external magnetic field. So when we make NMR instruments, we try to keep the magnetic field as homogeneous as possible, but with the iron in the sample, so you destroy that homogeneity. So your T2 will be shortened when you do the measurement. So that's not good for conventional measurement, because you're in the conventional sample, your T2 is in milliseconds to hundreds milliseconds range.
Yeah.
But for the unconventional, we talk about anything below 100 millisecond range. So it's much easier for the high frequency to play its role. That's the reason.
Okay.
So,
Thank you.
Some people are thinking high frequency got advantages, we can replace low frequency. No, that's not the case.
I just wanted to ask your expert opinion. I think maintaining the high frequency instrument will also be difficult, as you mentioned, with all these impurities that can impact the gradient.
Yeah, and the beauty part for the unconventional analysis is we don't care about exactly T2 values as like in low frequency, because people normally say, oh, we want to use a cutoff, right? T2 cutoff. So the T2 values sometimes has its meaning, but for unconventional, we try to get away from that. So that's another reason. Okay. Good. More questions?
Any other question? Okay. I had a question, but I think it was Sabia, the first question. So this inversion that you did was from the raw data, right? Like fitting the Gaussian and exponential functions to do the inversion for the raw data. Not
Okay.
for identifying like fluids after the inversion, right? Just
You're talking about these maps, right?
the previous one, yeah.
Okay. So in this case, we didn't do inversion. We just do the simple curve fitting. So we fit this curve into three functions: Gaussian, exponential 1, exponential 2. So just simple mathematical curve fitting. So you get T2, that's the position of the bar, and also the amplitude. So for this kind of early time analysis. So this is a good way to study the kerogen. And so I did not plot here. So the kerogen maturity is proportional to the ratio of these two. So I already had a paper published for that part. So you can use the NMR data to correlate with the so-called maturity of the kerogen. Try to understand the kerogen, and sometimes if people do a pyrolysis, it takes a long time, and doing this work is much quicker. So when we do this measurement on a few minutes measurements, you get it done. But for pyrolysis, you need to prepare a sample and then put in the machine, and it take hours to get the results. So sometimes we can get a quick measurement, use NMR, try to understand the properties of a kerogen, put it that way. And also the potential of the oil production. So you can see for this one, we can tell probably won't produce any oil. But for this two, or even this two, you have a lot of potential to produce oil. But the total volume may be not that high because oil already been produced. So this one probably a little bit too mature. And this is a kind of in the oil window, you can produce a lot of oil. So give you some indications to study.
Okay, thank you.
Okay.
We have time for another question. Okay, well, thank you very much, Harry, and everyone for coming to this session today.
Adia wants to have a question. Okay, you're welcome, and very, very pleased and to